So in the latter part of the electrochemistry chapter, we're looking at electrolytic cells. So this means we have to apply a certain amount of, we have to apply energy in order for the cell to proceed. And so these are going to be non-spontaneous cells. And so usually we apply a certain amount of current for a given amount of time, and that can cause the reaction to plate a certain amount of metal. So here we want to know how much time in hours required to produce 1,000 kilograms of magnesium with a current of 150,000 amps through molten magnesium chloride. And we assume 100% yield for magnesium. And if you haven't done so, make sure you look over the lecture notes for electrochemistry part 2, because there's a very good flow chart on how to solve electrolysis problems. And so again, we know that current is equal to charge over time. And so since we're looking for time, we need to know the charge and the current. So charge is in coulombs, current is in coulombs per second. And so if we know these two things, we can determine the time it will take to produce 1,000 kilograms of magnesium. So the current is given to us, it's 150,000 amps. Now to know the charge, that's our unknown. So once we find the charge, we can determine the time. And so charge is equal to the moles of electrons that have been transferred times the Faraday constant, which is 96,500 coulombs per mole of electrons. So if we know the moles of electrons transferred, we know the Faraday constant, we can calculate the charge that was applied. So to find the moles of electrons, we need to know the moles of substance, because there's a relationship based on the half reaction between the moles of electrons and the moles of substance used or produced. And once we know the moles of the substance, we get it from the mass of the substance. So if we know how much mass we want to produce, we can calculate the moles of substance. Then we can convert it to moles of electrons, and then ultimately find the charge. So the first step is to find the moles of magnesium. And so since we have 1,000 kilograms, we got to convert it to grams and then to moles. So this is the number of moles of magnesium that we have. So now that we found the moles of magnesium, we need to convert it to the moles of electron. Magnesium is being reduced from magnesium 2+ to elemental magnesium. So the reduction half reaction looks like this. So for every 2 electrons, we produce 1 mole of magnesium. So there's a 2-to-1 relationship between electrons and the substance. So now we can convert moles of a substance into moles of electrons using this relationship. So now we can find the moles of electrons. We simply just multiply the moles of magnesium by 2. We get the moles of electrons. Once we have the moles of electrons, we can find the charge. We multiply it by the Faraday constant. We get the charge in coulombs, and then now that we have the charge and we know the current, we can calculate the time. So it's this many seconds, and then we convert that to hours. And so it's about 14.7 hours you need to apply 150,000 amp current to produce 1,000 kilograms of magnesium. So again, this is one type of electrolysis problem when we're given the amount of metal produced and we want to know the time. Another way you can have an electrolysis problem is here we're looking about how much mass of metal is produced when we apply a current for a certain amount of time. So here we want to know how many grams of cobalt are deposited from a solution of cobalt-3 chloride that is electrolyzed with a current of 23 amps for 63.5 minutes. So again, here we're applying a certain current for a certain amount of time. How much cobalt is produced? So again, mass of substance is related to the moles of substance. If we know the moles of the substance, we can find the mass by using the molar mass. The moles of substance is related to the moles of electrons, so we know how many moles of electrons were transferred. We can know how many moles of substance were produced. Now we know from the reduction half reaction, since we're going from cobalt 3 plus to cobalt, that there are 3 moles of electrons for every 1 mole of cobalt produced. So there's a 3-to-1 relationship between electrons and cobalt. So now we know how many moles of electrons for every 1 mole of substance. If we know the moles of electrons, we can convert it to the moles of substance. Now to find the moles of electrons, we got to know the charge divided by the Faraday constant. So Faraday is a constant. We need to know the charge in order to come and determine the moles of electrons. So once we find the moles of electrons, we can find the moles of substance. To determine the charge, we need to know the time times the current. Now remember, current is coulombs per second. So time has to be in seconds when determining the charge. So we have the current 23 amps. We convert the minutes to seconds. We can determine the charge that was applied. So now we know the charge, we can find the moles of electrons. So simply dividing by Faraday's constant, we get the moles of electrons that were transferred. Now that we have the moles of electrons, we can find the moles of cobalt. Remember, it's a 3-to-1 ratio, 3 moles of electrons to 1 mole of cobalt. And then we can find the mass of cobalt. So here it's going to be plated about 17.8 grams of cobalt. In our last electrolysis problem, here we apply a current. We pass it through an unknown +3 ion solution for 73.8 minutes. It produces 37.7 grams of the metal. What's the identity of the metal? So here we apply a current for this amount of time. We produce this much metal. We want to know what's the identity of the metal. So again, to determine the identity of the metal, we need to know the molar mass of the metal. So we need to know the mass of the metal and the moles of the metal. And so the mass of metal is given to us in the problem, 37.7 grams. So we know the mass of metal, we need to know the moles of metal. The moles of metal is not given to us in the problem. So what we do know is the moles of the substance is related to the moles of electrons that were transferred. So if we find the moles of electrons, we can find the moles of substance. And the way we do that is from the reduction half reaction. So 3 moles of electrons produce 1 mole of the metal. Now to find the moles of electrons, we got to use this equation where the charge equals moles of electrons times Faraday constant. So again, moles of electrons is equal to the charge divided by the Faraday constant. Now to find the charge, again, current is equal to charge divided by time. So to find charge, we need to take current times time. So if we know the current and we know the time, we can find the charge. And once we know the charge, we can rearrange the equation shown here to solve for moles of electrons. Again, Faraday F is a constant. But we got to convert the time into seconds. Once we do that, we can find the charge. Once we have the charge, we can divide by Faraday's constant to get the moles of electrons. Once we know the moles of electrons, we know that 3 moles of electron gives us 1 mole of metal. So we can find the moles of metal, or M. Now we know the moles of the metal and the mass of the metal, we can calculate the molar mass. So this is 157 grams per mole, and if you look on the periodic table, you'll see that this is very similar to the metal gallium, Gd. So that would be the element that was used in this electrolysis reaction. So in nuclear chemistry, there are some natural radioactive processes like alpha decay, beta decay, positron emission. And so elements, when they undergo a radioactive process, they transform into a new isotope. And so the thing you have to remember about nuclear reactions or nuclear equations is that the mass number and atomic number are conserved. So whatever your total mass number is on the reactant side, you have to have the total mass number on the product side. Likewise, whatever your total atomic number is on the reactant side, you have to have that same total atomic number on the product side. So here, for example, we have hafnium-182. We produce an alpha particle. So this is alpha particle decay. So decay emissions means it's a product. And so you see here, alpha particle, which is similar to the helium nucleus, has a mass number of 4 and an atomic number of 2. So that means our unidentified product is going to have a mass number of 178. Because 178 plus 4 gives us 182, and it's going to have an atomic number of 70, because 70 plus 2 gives us 72. So then you would go on the periodic table, you would see which element has an atomic number of 70, and that would be Yb. And so that would be the isotope that would form when hafnium-182 undergoes alpha decay. So another type of decay is positron emission. So we produce a positron, which is, you could say, a positive electron. And so Cm undergoes positron emission. What's the resulting isotope? So again, what we have to look at is the mass number and atomic number. So for a positron, it has a mass number of 0. And so that means the mass number of our unidentified isotope should be 250, because again, the mass number is conserved. And then our atomic number on the reactant side is 96. On the product side, we already have a +1. So that means our unidentified isotope should have a atomic number of 95, because 95 plus 1 gives us 96. So again, you go on the periodic table, you look to see which element has an atomic number of 95, and it's Am. So again, the thing you have to remember is that mass number and atomic number are conserved in nuclear reactions. So whatever the total mass number and atomic number are on the reactant side, the same thing is going to be true on the product side.